In this video, I introduce a kernel Wasserstein distance from machine learning. A data set of n samples in a native space is denoted by X. The data in the kernel space phi is generated by nonlinear mapping function phi. The kernel trick avoids complex data handling in the kernel space and explicit computation of the mapping function phi. Instead, directly computes the kernel key from data in the native space. A positive definite kernel function key is associated with the mapping function phi so that the kernel function is equal to the inner product of phi x and phi y. A radial basis function is selected as a kernel function. The mean, mu, and covariance matrix sigma in the kernel space are estimated by using the mapping function phi. Kernel trick allows us to compute mu and sigma without knowing explicit mapping function phi. In machine learning, our goal is to measure similarity between two images. First, we use phi map the image to a kernel space, and then use the kernel trick to compute the kernel function in the kernel space. And then use two moments mu and sigma in kernel space to compute the distance between two input images. Suppose that X and Y are two probability spaces with measures mu and nu. C denotes the cost of moving one unit of mass from X to Y. And we found a mapping T from X to Y that minimizes the cost of this integral. L2 Wasserstein distance on mu and nu is defined as infimum of this integral, where pi is the optimal policy. This sigma is a set of joint probability measure pi on x by y, where mu and nu are marginal probabilities. L2 Wasserstein distance is based on optimal mass transport theory, in which we move the data in distribution 1 to distribution 2 with a minimum cost. Considering two Gaussian distributions, the nu1 and nu2 L2 Wasserstein distance is defined as a summation of two terms. First term is the squared difference of M1, M2, plus the trace of C1 and C2. Where TR is a trace, for example, for a n by n square matrix, A is a trace is a summation of his diagonal elements. In a special case, L2 Wasserstein distance is equal to square difference M1, M2 for C1, the same as C2. Suppose that two Gaussian measures Knu1 and Knu2 in the kernel space with the means mu and covariance sigma, respectively. To set up for sample data in the native space X and Y are associated with Kmu1 and Knu2, respectively. The L2 Wasserstein distance between two distributions is written as a sum of two terms. The first term we can calculate by using the kernel trick from a kernel function key. For a special case, sigma 1 is same as sigma 2. We have this L2 Wasserstein distance is just from the first term here. For more details, please check with these references. Thank you. Bye.